Let us look into the 11th lecture in module 3. In lecture 11, we are going to extend the chemical exposure index study as let us say 2, which is chemical risk analysis. In the last lecture, we discussed about the importance of chemical risk analysis and what a chemical exposure index can help us to do with, what are the prerequisites of conducting the chemical risk analysis to obtain the chemical exposure index. We have also understood the importance of the ERPG guidelines of different levels 1, 2 and 3, and we already understood that in a chemical engineering handbook for all hazardous chemicals different concentration as applicable to ERPG level 1, 2 and 3 are available in the literature. So, we said that one is interested to actually compute the airborne quantity of the chemical which is getting released in the atmosphere. Let us try to do that now. So, to estimate airborne quantity, which we call AQ. Obviously, there can be a possibility that the chemical getting released may be in the gaseous state, may be in the liquid state, it may become vapor depending upon the flash point temperature. So, let us say for gaseous release, AQ is given by 4.751 10 power minus 6 d square P A m W by T whole to the power half, equation 1, where A Q is the airborne quantity which is going to be in kg per second. P A is the absolute pressure which is in kilopascal, which can be the gauge pressure plus 101.35. mW is the molecular weight of the substance, of the material, T is the process temperature in degree Celsius. I converted that into Kelvin by adding this, and of course, capital D is the diameter of the hole in millimeters. Friends, it is important that we maintain the same units to compute the airborne quantity, because there is an empirical relationship where this constant is calculated depending upon the respective units in the given substitution. Okay. So, we compute AQ if we know all these input parameters. I can compute AQ if it is a gaseous release. For a liquid release, the steps are slightly tedious. So, step number 1 for liquid release, I have to estimate the total liquid release. Which can be given by L is equal to 9.44 10 power minus 7 d square rho 1 square root of 1000 gauge pressure by rho 1 plus 9.8 delta H equation 2, where rho 1 is the density of the liquid in kg per cubic meter at operating temperature. Pg is the gauge pressure, in kilopascal. For example, if you have an open tank, or an open vessel which is open to the atmosphere, then Pg is taken as 0. Delta H is the height of the liquid column measured from the release point in meters. L is expressed as liquid flow rate in so many kg per second, and of course, d is the hole diameter in millimeters. Once I know the liquid release estimate, which is the liquid flow rate from equation 2, they can compute then what we call Wt, which is 900 into L. So, step number 2, I want to compute the AQ due to flashing, the airborne quantity due to flashing. To obtain this, compare the operating temperature of the liquid to its normal boiling point. On comparison, if the temperature is lower than the boiling point, then the flash fraction of the liquid will be 0. It will not get flash at all. Okay. Otherwise, the flash volume Fv is given by Cp by Hv Ts minus Tb, equation number 3, where Tb is the boiling point temperature, in degree Celsius, Ts is the operating temperature, in degree Celsius, Cp is the average heat capacity of the liquid, which is expressed in terms of joule per kg per degree Celsius. Hv is called heat of vaporization of the liquid, which is given in joules per kg. L of course is the liquid rate in kg per second, liquid flow rate in kg per second. So, I am interested in working out the air quantity because of flash, that is what we are trying to find out, the flash fraction, which is given by phi Fe into L. L is already computed, we already know from step number 1. Fe is computed from equation 3. I can find the airborne quantity of a flash fraction from this equation. While estimating Fe from equation 3, that is the flash fraction from equation 3, if Fe is more than or equal to 0.2, then one can say AQ of flash will be straightaway equal to the total liquid flow rate itself. So, in that case we can say that no pool will be formed. Okay. Let us say this equation number with this condition, equation number 5. Interestingly, all the chemical properties of the other materials like Cp, Hv, Tb, Ts etc. are to be known. Interestingly, if the chemical is not listed, to find any necessary information, then in that case standard value of Cp by Hv can be taken as 0.0044. As we proceed further, as flashing occurs, some liquid will be entrained as droplets. Some of these droplets are quite small and travel, or they could travel with the vapor, while large droplets fall down to the ground and will be collected in a pool. So, large droplets will be collected in a pool, small droplets will travel along with the vapor. So, therefore, if 20% of the material flashes, the entire stream becomes airborne. So, there is an assumption that if 20% of the material flashes at the operating temperature compared to the boiling point, then it is assumed that entire stream becomes airborne. Therefore, no pool will be formed. So, that is for Fe greater than or equal to 0.2, one can say that airborne quantity will be equal to the liquid flow rate and no pool will be formed. So, step number 3, once the pool is formed, I want to estimate air quantity due to pool boiling. So, I would like to work out what is called the total mass entering the pool. Wp, which is given by the total mass entering the pool will be Wt into 1 minus Fe, equation number 6. And Ap will be given by 100 of Wp by W by rho L. And AQP, that is the airborne quantity which is coming from the pool boiling, will be given by 9 10 power minus 4 AP, which we compute from here, this is 0.95 multiplied by molecular weight into PV by T plus 273, equation number 7. Wt in this equation is the total liquid released, Fv of course is the fraction released, which we already computed. Wp is the total mass entering the pool, maybe in kgs. Rho 1 or rho L is the density of the liquid, in kg per cubic meter. Ap is the pool area in square meters. Mw of course the molecular weight of the material, and Pv is the vapor pressure, what we have here is the vapor pressure of the liquid at pool temperature. Which generally the pool temperature is in degree Celsius, and T is the pool temperature. In again degree Celsius. So, we can easily find out the airborne quantity of the pool boiling, which is coming from here. So, step number 4, the total airborne quantity now will be actually equal to airborne quantity which comes from the flash plus airborne quantity which comes from the pool. Let us take equation number 8. If the airborne quantity what you compute from equation 8 is more than liquid rate L or liquid flow rate L, then airborne quantity is equal to L. It cannot be of course more than L, okay, in any case. Then one can compute the chemical exposure index. So, the equation is chemical exposure index given by 655.1 multiplied by the airborne quantity what you computed by the ERPG concentration 2 for the liquid or for the hazardous material. If the Ci computed from above equation exceeds 1000, then set the index as 1000, it cannot be more than 1000. As I told you, while estimating the chemical exposure index, one also takes care of the weather conditions, Pascal stability, wind velocity, speed, direction, propagation, etc. So, Ci calculations assume that wind speed is about 5 meter per second. It also assumes normal weather conditions ERPG value what we substitute here required to be done in milligram per cubic meter, because ERPG may be given in other forms of concentration also. ERP is actually nothing but the concentration which can be sustained by an exposed person for a specific period of 60 minutes, either having no damage, either having no irreversible damage, either has a reversible damage, but not a fatality. That is level 1, 2 and 3 respectively. So, you have to substitute that value in milligram per cubic meter. Please look at the concentration available in the tables of chemical engineering handbook. Sometimes it can be of a different unit. You have to see ERPG value for a specific concentration in milligram per cubic meter, because all these constants are taken care of in this number. So, we have to substitute only these exact units. Now, as I said in the beginning, one is not interested alone in finding out the exposure index. Of course, one is curious to know the exposure index, because by this you will know the risk value, but we are not interested and stop here. We want to compute the hazard distance. So, to compute hazard distance, hazard distance Hd for a specific concentration can be given by 6551 AQ by specific ERPG value. Suppose if you really wanted to know the hazard distance for ERPG level 1, then substitute ERPG level 1 concentration here. If you want to know for ERPG level 2, substitute the respective concentration here and so on. Okay. So, you have to accordingly estimate the hazard distance for a specific concentration. Of course, the airborne quantity what we computed from equation 8 will remain unchanged whatever value ERPG you are trying to put. Okay. If the hazard distance exceeds 10,000 meters as computed from equation number 11, then set hazard distance as let us say 10 kilometers. That is the maximum distance we can have. It means in general water may be the chemical which is hazardous in nature. You can always locate the residential units, the commercial areas etc., from away a radius of about 10 kilometers from the central point which is expected to release the chemical. So, after 10 kilometers radius you can always locate any plant is going to remain non-hazardous. Okay. So, once you compute the hazard distance for different ERPG concentration, one should then prepare a summary sheet. A typical summary sheet is shown on the screen now. Please look at the data sheet shown on the screen. This is called chemical exposure summary sheet. You have to enter the name of the plant here, enter the location of the plant, indicate the chemical for which you are doing the CA study. Also try to enter what is the total quantity of this chemical present in the plant. Identify a single largest containment which has got this chemical stored in the plant. Note down the temperature operating and the pressure operation of the containment here. Try to see what scenario you are going to evaluate. We will talk about the scenario possibly after we complete the discussion here. Estimate air quantity AQ, release rate may be in kg per second or maybe in different units, pounds per minute. We are interested in kg per second. All equations I gave you on the blackboard were only on kg per second. So, estimate the airborne quantity in kg per second, either it is a liquid or a gas. Try to enter this, we have the respective equations available with me. Then calculate the chemical exposure index which I have given you in equation 10 on the blackboard here, equation 10. Use this and estimate CL. Please understand, CA index is always related to concentration of ERPG 2 level, okay, that is very important. So, enter the CA index here. Of course, for a given chemical concentration, for a given chemical in the plant, enter the concentration values of ERPG 1, 2 and 3 in milligram per cubic meter, and using equation 11 the corresponding ERPG concentration substitute for that and get the hazard distance in meters and enter the hazard distance in meters here. Then based upon this you can always give a recommendation what we call Dow property line. So, please recommend what could be the distance in meters beyond which public can be located, other in company can be located, non company business can be located. So, interestingly you got to fill up this and then assess what would be the consequence on these if the distances are closer than the distances for a specific concentration arrived from this equation. So, this summary sheet will tell you completely how to estimate a chemical exposure index, how to estimate the hazard distances and what would be the consequence of public, property etc. lying within this hazard distance for a specific concentration of ERPG level, which is available in the chemical handbook for all hazardous substances. You must also say who has prepared the report, who has reviewed the report, what was the date at which you reviewed the site and what additional recommendations you made and on what capacity you made. So, this report is a legal document which is stocked and stored in the industry. So, friends, after preparing chemical exposure index, one need to prepare the mitigation checklist. So, after completing chemical exposure index, one should also prepare mitigation checklist. A typical mitigation checklist can be seen on the screen now. Please look at all possible risk reducing factors like all pressure vessels and relief system devices are properly registered, all hoses inspected, all operational controls and systems designed and routinely tested for no failure, critical instrumentation program is up to date, operating discipline complete and up to date, vapor detectors installed and working properly, appropriate engineering specifications applied properly, relief vents and toxic containers are designed properly, etc. So, look at all these risk reducing factors and keep on preparing a checklist whether they have been done or not done, maybe yes or no only, maybe a tick mark or a cross mark. So, based upon this mitigation checklist, one will have fairly an idea which is given along with the chemical exposure index sheet. So, one will get an idea about the risk envisaged because of the accidental release of the chemical from the plant onto the environment. Now, there are furthermore discussions about this ERPG values, because ERPG values actually talk about the concentration of the chemical or the liquid or concentration of the material in terms of its acceptance level, on human. Okay. If the established ERPG level are not available, maybe the chemical is not listed and ERPG level, ERPG for level 1, 2 and 3 concentrations are, let us say, not available. In that case what do you do? Because without knowing the ERPG concentration, you can neither calculate the hazard distance nor the chemical exposure index, because you need the value. There may be certain chemicals, certain mixture, certain composition whose ERPG level values of concentration may not be given in the table, listed in the table or in the handbook. In that case what do you do? Let us say for example, if ERPG 2 concentration is not available, which is required to compute the chemical exposure index, because please understand friends, chemical exposure index is computed based only on ERPG 2 level concentration. Okay. Then one can use the exposure guidelines given by various international agencies, recommended by let us say Dow, IGH, American Society or Congress of Industrial Hygienists. They have given the TLV limits, threshold value limits. One can also look at American Industrial Hygienes Association, where they have given wheel values. So, one can look at these values and use them as an alternate substitution for ERPG 2 for a mixture which is not available. One can also use short term exposure limit, that is TEL values of the mixture, or time weighted average sealing value of the mixture in place of ERPG 2. So, that is as far the discussion on ERPG 2 is concerned, which is required to compute the chemical exposure index. Now, to compute the hazard distances, you may require ERPG of all the levels, okay? ERPG 1, 2 and 3 all will be required, because hazard distance can be estimated for all concentration. So, if ERPG 3 is not available or is not listed for the mixture in the table, then one can assume ERPG 3 as 5 times of ERPG 2. If ERPG 1 is not available or not listed in the table, then one can either find out the one can either use odor threshold value OTV, that is called odor threshold value available in the literature in place of ERPG 1, or one can use 1 by 10th of ERPG 2 as ERPG 1 in case they are not available. As being explained and understood, we all know that chemical exposure index is computed for a specific scenario. So, the foremost job in a given plant is to identify the scenario, or if you can identify more than one scenario, you must compute CEI for each scenario. So, the purpose is to determine which process piping or equipment has the greatest potential for release of significant quantity of acutely toxic chemicals. So, one should evaluate all possible scenarios to compute or to identify the worst possible scenario whose CI is maximum, or on the other hand which can give the maximum airborne quantity, that is what it is. all process conditions such as temperature, pressure, physical state, pipe size should be considered, so that they have a significant impact on the airborne release rates. So, please understand the factors which will have significant impact or significant influence on estimating airborne quantity could be temperature, that is operating temperature, operating pressure, then weather conditions, then physical state of the chemical, then of course the pipe size, height of release. All factors will influence significantly the airborne quantity, which in turn influences the chemical exposure index value what you obtain. So, interestingly friends, the whole exercise of CEI amounts to identifying various scenarios. So, in a given process plant, you must try to identify various scenarios. For each scenarios, we must obtain the chemical exposure index, then try to identify the worst possible scenario whose CI index is the maximum, or alternatively the scenario which can give me the maximum airborne quantity. So, in the next class we will take up examples and identify scenarios, work out CEI value and AQ values for all the scenarios, and then we will compare the scenarios and say amongst the identified scenarios which is having the maximum airborne quantity or the maximum CI index. Okay. So, in this lecture we learned how to actually do a chemical exposure analysis, how to estimate chemical exposure index which is given by the Dow's method. We have also understood how the gas and liquid concentrations can be equally handled by different equations which are empirical in value. What are the factors that can influence the hazard distances? What are the factors that can influence the chemical exposure index or AQ value? And what are the factors which can influence the ERPG values which are available in the literature? If ERPG values are not available, what are the alternative values for ERPG 1, 2 and 3 to estimate the appropriate hazard distances? So, ultimately chemical exposure index will give me an equivalent hazard distance, beyond which if the public is placed, it will have no effect even though the chemical may be released on any specific rate and remain as airborne. Thank you very much.